Congratulations for surviving Topic 2. In comparison, I think you'll find Topic 3, and this is our first lesson in Topic 3, much less intense. Technically, Topic 3 a lot of times is rolled into Topic 2. In fact, all of these are in the same chapter in your book. They're all in, I think, Chapter 3 in your book. However, I always split these three topics, these implicit differentiations, derivatives of inverses, and related rates into their own little mini units. So Topic 3 actually only has three little subtopics, sub-goals that we cover. It'll take us about 8 or so class periods to get through these three, but I like to slow down because these are kind of bigger concepts. Implicit is all over the place. Related rates is one of our first real-world applications, and then inverses is just a little bit tricky. So we take this a little bit slower. We give between 2 and 3 days for every little subtopic here, and I want you really to feel confident on these three. I think the other, everything we did in Topic 2, you'll practice those over and over and over again, small things, product rule, chain rule. Topic 3, though, these guys are really, you need to get them the first time through, and we'll practice till you get it, because we don't maybe practice them as much later on, and I want you to be really confident at the end of this. So without further ado, let's jump into it. Day 28 is our introduction to implicit differentiation. Your goal is to find dy dx, which is, of course, the rate of change of y as x changes for each function below. And I'll go through, actually you should be able to do all of these, I think. So go ahead and with your group or on your own, find the derivative of each of these, and then we will discuss. Ready, set, go. All right, well, this first one, this ddx right here of y and ddx of x squared, we need to remember that ddx is an action. It means take the derivative of an equation with respect to x. Now, technically the d up here really is more the differential, not the derivative, and we're going to learn more about the differential down the road. For now, again, we'll just assume it means take the derivative. And we talked about how this is kind of an abuse of the notation, but we make it work anyways. And so when we take the derivative of y, we go through and we can actually move the y up here, and we can say that this becomes dy dx. And then over here, ddx of x squared, well, we know that becomes 2x to the first. And if you want, you can multiply by the derivative of the inside, which is 1. But, of course, hopefully you just said that dy dx equals 2x. Moving on to these next two can be a little bit trickier. Y squared equals x, and x cubed plus y cubed equals 8. Now, my guess is what you probably did here is you probably went through an isolated y first. I mean, that's what I would have done. So we would, of course, introduce a square root, and we know that whenever we introduce a square root, we need a plus minus here. So it becomes y equals the plus minus square root of x. Or using our algebra, no calculus yet, we could rewrite this as x to the 1/2 power with a plus minus in front. Now, it'll turn out that that plus minus can really be kept all the way through this problem. Just realize that it's there and don't let it overwhelm you. So when we go through and find this derivative, or when we do ddx of each side, take the derivative of each side, we do need to keep that plus minus attached to the x. And so we end up with this dy dx equals plus minus 1/2 x to the negative 1/2. Or continuing through, and hopefully you've done this derivative enough so that when I skip right to our answer, it doesn't shock you too much, 1 over 2 root x with that plus minus. Okay. Now, what does this plus minus actually mean? Well, it tells us that for every x value, you actually have to do two equations. You have to do one where you find the positive answer and one where you find the negative. And so that tells you that our graph's going to have a bit of symmetry. For an x value, there's going to be two different rate of changes, which probably means if you picture an xy axis, here's our x value. If there's some rate of change up here and another one down here, it probably means that this graph isn't a function. And in fact, y squared equals x, I did my parabola backwards, but is a sideways facing parabola. So you can see for every x value, for example, this x value is, let's say, 1 up here and down here, there are two corresponding y values, which means there'll be two different slopes, one slope in a positive direction, one slope in a negative direction, hence that plus minus. All right, let's go ahead and take a peek at the last one. For our last one, I think, again, you'll probably want to isolate that y cubed. Okay, and then cube root to undo everything. Remember, when we introduce an odd indexed root, we do not want to do a plus minus. There's only one answer for these, not two. And we could, of course, rewrite this 8 minus x cubed to the 1/3 power. ddx of both sides is going to give us dy dx equals 1/3 8 minus x cubed to the negative 2/3, but don't forget the chain rule. Derivative of the inside, well, let's do it all at once. Let's say the derivative of 8 is 0 minus 3x squared. And again, if you wanted to clean this up, you don't have to, but if you wanted to, you could. The negative 3x squared will stay up top, the 1/3 in the denominator, and then the cube root of, we'll extend that fraction line, the cube root of 8 minus x cubed squared. And we have our wonderful derivative. Now, you might have noticed that some of these derivatives are pretty messy. I mean, they're doable, but having to deal with this plus minus here, or having to deal with this extra chain rule and the weird negative exponent, and having had to do algebra at the beginning is a little bit obnoxious. So let's go ahead and get into the idea of implicit differentiation, because what this is going to do is really just give us a different way to take a derivative that's going to be more efficient for a lot of the equations that we deal with, especially ones that don't have y isolated here. Okay, and here's our main lesson for today. Let's start by talking about what it means for something to be implicit. If something is understood implicitly, then it means that the idea is implied and you still understand it, even though it's not maybe actually said out loud. It's something you understand implicitly. For example, I implicitly trust my math teacher. I can't explain it. He just seems like a good human, a little self-centered, but seems like a good guy. Cool. If something is stated explicitly, it's written out or it's said out loud, and that's our difference between implicit versus explicit. In math, an implicit function is where the dependent variable, and a lot of times our dependent variable is y, is not isolated. So which functions in the opener are implicitly defined? Well, that would certainly be b and c. Now, we did eventually find an explicit definition for them, right? When we isolated y, these are our explicit forms, but in blue up here, I'll show you the implicit forms. Okay. Now, so far, really all the way up through today, we've only taken derivatives of functions which are defined explicitly, as a function of x. So usually an explicit function is given as y equals f of x, which we read as y is a function of x. Now, sometimes you could call your functions, and it says strange numbers, it probably means strange letters or variables, whatever you want it to say, such as m equals f of t, which could be maybe money is a function of t time spent at a job. You can also go ahead and change this f symbol here. I really don't like to do that, though. I think it just adds confusion as to what that symbol means. I like having f there because I really like to think of f as standing in for a function. It's all the stuff that's happening to this independent variable. The only time I really change that is if we have two equations that have the exact same independent and dependent variable, and things might get confusing, right? So, for example, if you were dealing with an equation y equals a function of x, where maybe the function of x is something like 2x plus 3, and then you're dealing with another function of x, well, then that would be really confusing. You're like, aren't those the same? So here you might want to redefine this as like g of x, and where you're like, well, g is just the fact that x is getting plugged into a function, right? So these aren't really variables. They're just telling us that there's a function involved. Instead of changing the f to a g, I'm much more of a fan of just saying, let's go ahead and just say it's some function of t. Of course, then people are like, well, is the function the same? Did you just replace that with t? And the answer is sometimes yes, sometimes no, but it'll be clear enough in the problem, so don't let it stress you out too much. But there's just your quick rundown of function notation. You should, of course, remember that f of x and f of t are pieces that are standing in for an equation, right? So instead of writing y as a function of x, where the function that's acting upon x is 2x plus 3, you could, of course, put all of this together and just say y is equal to 2x plus 3, right? There's nothing wrong with that. But realize that f of x, of course, is standing in for 2x plus 3. Okay, so for example, let's look at y equals a function of x, where the function that's acting upon x is 12 times x minus 3. Therefore, of course, instead of saying y equals a function of x, you can say y equals 12x minus 3. Now, of course, since y is equal to 12x minus 3, if you saw another function, such as y equals z, then you could replace y with 12x minus 3 to get 12x minus 3 equals z, right? Just lots of substitutions here. Now, keep that in mind, because we're going to come back to it later on. But let's go ahead and talk about this implicit versus explicit form. For example, if you're given the equation x squared plus y squared equals 4, then let's go ahead and write the above equation in the form y equals f of x using function notation. Well, in order to do that, you do actually have to isolate y first. It needs to be y equals all the stuff acting upon x. And this is also a nice giveaway that x will be our independent variable, the thing that we are varying to find y. So we're going to take our x squared plus y squared equals 4. We'll probably want to subtract the x squared, and then, of course, take the square root of each side. Nothing too surprising here, but don't forget that we do need the plus minus. All right, now is this a function? Well, there's a couple ways you could know if this is a function or not. You could know what the graph of this looks like, but you might not know what the graph of that looks like. But then you could maybe understand what this is telling us right here. This is telling us that for every x you input in here, you're going to get two answers, one positive, one negative. So maybe think about something where you have an x, and then you have the same x. Well, here you're going to get some negative answer, and here you're going to get some positive answer. All right, well, is that a function? Well, I think no, because of course one of our basic definitions of a function that you get in Algebra 1 is that you can't have different outputs for the same input. That would just make life confusing. If I said input 2 into the function, and you're like, or no, actually, maybe let's go the other way. You're like, the answer is, well, no, let's go the first way. You input 2 into a function, and they're like, what's the answer? And someone's like, it's 4. Someone else is like, no, it's negative 4. Well, you don't want there to be confusion as to the answer out of an equation. And if there is confusion, like in this case, someone says negative 4, and someone else is like, no, it's positive 4, but they're both right, then bad things happen. So we can hopefully very quickly see that we are not going to be a function. There are other ways to check this as well, and that's just a real quick rundown. So it says, describe the graph of the equation. Well, I actually have the graph pulled up for you over here. Here is x squared plus y squared equals 4. Shouldn't shock you. This is a circle. We should remember that when our coefficients match in front of x squared and y squared, they're both 1 here. This makes a circle. And 4 really should be written as 2 squared. It tells us we're centered at 0, 0 with a radius of 1, 2. Okay, 2 squared, 1, 2, right? Nothing like that. Nothing too terrible. Cool. Now, we went ahead and found the explicit form of this implicitly defined function. If you forgot the plus minus and you just had a positive, you'll only get half your circle. Once you add in the negative, you'd get the other part. We should also realize that plus minus doesn't mean that there's one function happening here. This plus minus is just lazy mathematician speak, right? This plus minus really means we need to graph both y equals 4 minus x squared, and we need to graph negative 4 minus x squared inside a square root. And it's two separate equations. So we started with one equation, and in order to write it explicitly, we had to write it as two separate functions, which is obnoxious because it really means two separate derivatives. And although sometimes it's easy enough to keep the plus minus in the derivative and you're like, great, I just got one answer, even though technically you got two, it's not always that easy. So hold that in mind too. Realize that our implicit form is much nicer than our explicit form in this case, and in fact that is the case many times. And then we need to do one more piece before we get into our implicit differentiation. And that is realizing that the chain rule never goes away. And I'm actually going to show you two ways to deal with this, two ways to understand this. One of them is not mathematically great, but that's okay. So let's look at both ways. So the first method is I'll just work straight across. I think there's enough room here. If I say take the derivative of x, and you actually move the x up here, this is something we haven't talked about yet, doesn't it become dx divided by dx, which is just anything divided by itself? That's just 1. Isn't the derivative of x 1? Well, compare that to if you were asked to take the derivative of y. Move the y up, you get dy dx. Nothing cancels. We can't cancel the d's. That means change in. We can't stop changing. And we get our final answer of dy dx. And remember, although we've called dy dx the derivative, really it's measuring how fast y is changing as x is changing at an infinitely small rate. But for now, we can think of this as just the derivative of an equation called y, where the independent variable is x. And if I continue through here, now what if I did d dy of this equation? Well, bring the x up. This becomes dx dy, and that's as far as we can go. So notice in this case, the derivative of x is not 1 because it doesn't match the variable in the denominator. What this is telling me is we have some equation called x, where x is the output, and we're seeing how that output variable changes as our input variable changes, like y. Right? Now, this would maybe be an equation like x equals 7y minus 2, where we have our dependent variable, our output, and we have our independent variable, our input. It's just backwards from normal. Of course, that also means that we should be able to do d dy of y, and that becomes dy dy. Oh, that's just 1. So realize then that we can absolutely use different variables down in the denominator of this dd something, this derivative operator, and anytime that variable matches the 1 right here, we're going to get an answer of 1. Now, I do want to go about this one other way. So take a look, and hopefully you wrote kind of small here. Let's go ahead and take the derivative of x to the first power. Well, the derivative of x to the first power is, of course, 1x to the 0th times the derivative of the inside. But we know that the derivative of x with respect to x is 1. So as we clean everything up, we get 1 times 1 times 1, right? Anything to the 0th is 1, which just gives us 1 as a final answer. You're like, wow, that is overly complicated. And you're right. However, there is a reasoning to my madness. So let's look at one more. ddx of y, well, we're going to take ddx of y and think of it as y to the first. So this becomes 1 times y to the 0th times the derivative of y. But we know that the ddx of y, we need to bring the y up and it becomes dy dx. Nothing cancels out here. And so we end up with 1 times dy dx, which is, of course, dy dx. And maybe it should be worth noting that I should have done that over here too, that this 1 here really is ddx of the inside, which is dx dx, which is where that 1 comes from at the end. Maybe that's a better way to think about it. Okay, let's look at two more. dy of x. Well, let's see. dy of x to the first power. Okay, this becomes 1 times x to the 0th times the derivative of x with respect to y. The derivative of x with respect to y. So this becomes 1 times d, whoops, I'm so used to doing it the other direction, I've done it twice now. dx dy, which is, of course, dx dy. And last but not least, dy of y. dy of y to the first power is 1 times y to the 0th times the derivative of y, chain rule, dy dy, because of our denominator over there, which is 1 times 1, which is, of course, 1. Now, again, this is kind of a silly example, and we're really kind of going in circles here, but this whole process is going to become very useful on our next page. So let's take a look. We did find on the previous page that we found the explicit form of this circle formula. So what we're going to do is we're going to take the derivative of each one. And then we'll come back to the other questions. Now, I said take the derivative. I really shouldn't have said that. I want to find dy dx for each of these equations. All right. Now, why am I saying find dy dx and not the derivative? Well, maybe it will be easier to show you instead of tell you. So let's go ahead and actually, why don't you work through this first one? You should be able to take the derivative of this, no problem. And then we'll talk about the second. So ready, set, go. All right. So as you worked through this, and it shouldn't be too terrible, we get dy dx on the left side, or at the y comes up, and on this one, I assume we've realized that this is plus minus 4 minus x squared to the 1/2 power. So it becomes plus minus 1/2. Inside stays the same. That's our chain rule in action, but we reduce the power by 1. Because we kept the interior the same, we need to multiply by the derivative of the interior, which is 0 minus 2x. And then technically you could stop there, but I know that we're going to have to clean this up later on. So how can we clean this up a little bit? Well, 0 minus 2x is negative 2x. The 2 that's in front is going to hang out in the denominator. And then this is going to become the square root of 4 minus x squared. Forgot my little cute plus minus out front. And then I think we can even take away these 2's, right? So cleaning this up just a little bit more, I think we end up with plus minus x divided by the square root of 4 minus x squared. It's not a beautiful derivative, but it is the dy dx for this equation. All right, now let's take a look at our implicit form. Well, implicitly, what we're really going to do here is we're not going to do any algebra at the beginning. Implicit differentiation really just means take the derivative as a function is defined implicitly as it lies. So whatever it is, we're not going to move anything around. We're just going to take the derivative straight through because we have that ability. So let's take a look here. And I'm going to use the chain rule on both of these because I think it's really, really important. And it's going to be like the chain rule that we did on this previous page. We're like, oh, that seems silly. I promise if you think of the chain rule, you won't screw this up. Because although implicit differentiation is not very difficult, it's no harder than anything we've done so far, people really start to confuse when the variables match and when they don't, and that throws off their answer. So let's take a peek. Let's do the derivative of x squared first with respect to x. So that's going to become 2 times x to the first. That just took, so now I know the derivative of x squared is 2x. I do, especially when it's ddx. However, going this extra step I think really will help you here, especially when we get to other variables. So ddx of x squared was 2x to the first, but I kept x the same. So I do need to multiply by the derivative of x. The derivative of x with respect to x is going to be dx, and then the x moves to the top. Right? So if I clean this up, of course, it becomes 2 times x times, well, dx divided by dx is 1. So, of course, all of this just becomes 2x. And you're like, duh, vindication. The derivative of x squared is 2x. We knew that. Why did you take so long? Well, please allow me to demonstrate. Let's go ahead and do the derivative of y squared. This becomes 2 times y to the first power. You're like, of course, no surprises there. It's just 2y. But is it? Because when we multiply by the derivative of the inside and we use this same piece, and I should really use the same colors here to show the similarities, it becomes ddx, but the variable in this case is now y. And so if I clean this up a little bit, right, this becomes 2 times y, and we can't simplify this derivative, and so it stays dy dx. A lot of times you'll see people write that without the multiplication in between just to save some space. So although the derivative of x squared with respect to x is 2x, the derivative of y squared is not 2y. It's 2y times dy dx. And let's finish off the right side. The derivative of a constant, regardless of what's down here, is always going to be 0. Okay. Well, am I done? Well, no. I took the derivative of both sides of the equation, but I wanted to find dy dx, not the derivative. I want to find what is dy dx, and currently dy dx is implicitly defined in this equation. You are almost always going to want to explicitly define it. But what does that mean? It really just means let's isolate dy dx. And in fact, the reason we're really going to do that is because we want to compare our two derivatives and see if they're the same or if they're different. I mean, we have the same equation. Shouldn't they be the same? So let's see, isolating over here, I think we'll probably want to subtract that 2x first. So I get 2y dy dx equals negative 2x. And then we can divide by the 2y. So we get dy dx equals negative 2x divided by 2y. And in fact, I think we can even simplify further, can't we? We can, right, reduce our 2's. So we get derivative dy dx equals negative x divided by y. Now look at the comparison of derivatives here. the derivative on the right, to me, seems way nicer than the derivative on the left. The derivative on the right has no plus minus. It has no square root. It just has the x-coordinate divided by the y-coordinate. And so, for example, let's pick a point that's on this circle. Let's see. We were using x squared plus y squared equals 4. Let's use the point 2, 0. And I think if you plug 2 and 0 in here, don't we get 4 as an answer? So 2, 0 is on my circle. Now imagine I wanted to find the slope at 2, 0. Oh, that's not going to be a good one. Apologies. Let's do something a little bit more crazy. Let's try something like this. Let's try, how about the square root of 2 and the square root of 2? Square root of 2 squared is 2 plus 2 is 4. Yeah, square root of 2 comma square root of 2 is going to be on our circle. Let's try to find the slope at that point on each one. Well, if I wanted the slope down here, if I wanted to find, take the slope of the point square root of 2 comma square root of 2. Well, look at the math I'd have to do. Plus minus square root of 2 divided by the square root of 4 minus the square root of 2 squared. And that's very doable, right? We can get our plus minus. Square root of 2 is not going to change over here. This becomes 4 minus 2 over the square root of 2. So I think we're getting plus minus 1, right? So I mean, that's not that bad, but it's not great. And notice that square root of 2 comma square root of 2 is actually a single point. But with this plus minus in here, we actually got two different slopes. And how can a single point have two different slopes? So what ends up happening is you'll have to realize, well, only one of these, either the positive or the negative, will go with there, and then you'll have to work through it. Now, let's see what happens if I try to find that same slope of my implicitly found derivative over here, square root of 2 comma square root of 2. Okay? All right, negative, ooh, well, this one's weird because it has x and y in the problem, but that's easy enough, right? I have my x coordinate here and my y coordinate here. This is a derivative with two independent variables, two inputs, but we have two inputs in every point because a point has, two pieces, the x and the y. So negative square root of 2 divided by the square root of 2, the y coordinate, and of course those cancel and leaves us with negative 1. Cool. So what does that tell us? Well, it tells us at the point square root of 2 comma square root of 2, the slope, the derivative, the instantaneous rate of change is negative 1. Now think about what we did here. Which one of these would you have rather done? To me, I almost certainly would have rather done this one. Of course, we did get the same answer. So why do these two look so drastically different? Well, they actually only differ in one very small spot. I think they only differ really in the denominator, the plus minus in the denominator, I guess, so 2 spots. Of course, this one has an x, this has an x, this has a y, and this one doesn't, which to me suggests they substituted something in for y. What did they substitute? Oh, right, don't forget that y is equal to plus minus 4 minus x squared. So couldn't I replace y with the plus minus square root of 4 minus x squared? Of course you could. And then you actually get the same equation. You're like, wait. That one has a negative x, and this one has a positive x. That's true, but the plus minus is just going to swap the signs anyways. So whether you have a negative or not isn't actually going to affect the final answer. So they really are the same at this point. Now, generally, if you have a nicely defined implicit function, right, something like this that doesn't have square roots, doesn't have a plus minus, taking the derivative and isolating dy dx is almost always going to be nicer this way than it is if you have an explicitly defined function with square roots, with a plus minus, with something like that. So our main focus for the next while is to really only do implicit differentiation. And in fact, although in this case you could find the explicit form, you could isolate y, I think maybe that's not the case for every one of these. Right? For example, if you look at this one down here and I said isolate y, and I'm going to erase this so I probably wouldn't write anything here, you could definitely subtract your x squared, but then you're like isolate y. What do I do here? Well, you can't add 2y over to this side and expect to still isolate, because then this 2y is stuck inside the square root and you won't be able to move all the y's to the same side. You can't factor out a y like this. I mean, you can, but then you can't make two different equations because you can only do that with our zero product property if we're equal to 0. You couldn't divide this over either. So really it becomes pretty tricky. You might remember how to complete the square out of here, and then once you complete the square, you can isolate y in this situation. However, on this one, I think you're going to be SOL here, right? I think our y's are not going to be easily isolated at all. So in fact, there are many equations where you can't find a nicely defined explicit formula. And so taking the derivative implicitly is much easier. So we'll go ahead and do these two together, and then give you a couple to try on the back, go through it, and we're done for the day. So we want to find dy dx, and the important piece to realize is that means we're taking d dx of this equation. It's always important to identify what you're taking the derivative with respect to on both sides. So we're taking d dx of x squared plus y squared minus 2y equals 4. All right, well, we'll go a little bit quicker this time. We know d dx of x squared is 2x, and we saw before that d dx of y squared is 2y dy dx. But how do we deal with this minus 2 times y? Well, probably the easiest way is to do minus 2, that's a constant that's multiplying, and then think of d dx of y after. And I'll come back and finish that derivative in a hot second. So the right side d dx of 4 we know is 0. So nothing too much to clean up here. I am going to move this 2x to the right side. I've done this problem several times, and I know we'll have to do it eventually, and I just hate rewriting something when I could have done that in a previous step. So minus 2, and then let's go ahead and actually take the derivative of y. Well, to take the derivative of y, and it's basic, we can just bring the y up and say this is dy dx, and then think, does anything cancel? No. And so we end up here. Now that's very different than if this had been, and I'm going to erase this so don't write it, if they had said take the derivative of negative 2x, at this point you would have said that's easy, that's negative 2. Well, it's really not. It's negative 2 times dx dx, which is negative 2 times 1, which is negative 2. However, we need to realize the similarities between these two to make sure we don't make any silly mistakes. Negative 2x becomes negative 2 times 1, which is just negative 2. But that doesn't happen when we're doing the derivative of a different variable, not x. All right, now what? Well, I said I moved the 2x and then forgot to write it. There we go. Now if we want to isolate dy dx, you might be a little worried because you're like, but two terms have dy dx. Of course, you would never forget how to factor, right? There's a wonderful YouTube video, Teach Me How to Factor, that'll maybe refresh your memory on factoring if you would like. You can always sing it to yourself too. Teach me how to factor. Teach me how to factor. But let's finish this off. We factored out dy dx from each of these, and now I think we can divide over my 2y minus 2 to have our derivative. This is our derivative function. You'll notice that it has both x and y. It's a derivative function with two inputs, an x and a y, two independent variables. And honestly, I would probably go a step further too. I think, divide everything by 2. So we get negative x divided by y minus 1. That looks a little bit more clean to me. And we're done. Right? So instead of having to go through and isolate and deal with weird square roots, we get a pretty darn nice derivative. In fact, I think the derivative is maybe even nicer than the original function. All right, B is on here, and it's going to seem like an unnecessarily large amount of work, but it's on here because this tends to be the most common implicit derivative that I see on the AP exam. Like once every other year, there's always implicit on there, but they love this type of problem. And I can honestly understand their reasoning because this type of problem uses so many different rules that they're like, this is the coolest. However, it's a bit of work. So let's see what we can do. We will again, and you're going to need a lot of room here, a lot of room. So definitely write small. And you're like, but this seems so nice. It's just sign and a couple of variables. You're right, but it has to do with how the variables are attached. In particular, realize it's sine of 3 times x times y. And you can put those times wherever you want. We'll address that in a second. So let's take our derivative. d dx of y, bring the y up, it is dy dx, nothing crazy there. But the derivative of the right side is a little bit weird. We hopefully see that this is a chain rule, so let's do the derivative of sine first, cosine. And then, of course, we have to keep the inside the same. So are we done? No, sadly, we are not done here. And we know we're not done because we haven't done the derivative of the inside yet. So to do the derivative of the inside, we need to multiply by the derivative of the inside. But then we need to think. We have two variables attached by multiplication. And whenever you see that, you better be thinking product rule. So in fact, because I want to show that the product rule multiplies times all of this, I'm going to use a bracket. You could just use a big parenthesis or parentheses too if you wanted. I'll even set up the product rule. We know it's going to be set of parentheses, plus set of parentheses, set of parentheses. All right. Then the second question becomes, well, how do we do the product rule of 3 times x times y? Shouldn't we do like a product rule of 3 functions? So like 1, 2, 3 plus, and so on and so forth. No, you don't need to do that because this is just a constant. So you could either factor the 3 out and you could keep the 3 just hanging out here and put it back in at the end, or you could treat this as the function 3x, which is what I'm going to do, and the function y. So let's rock and roll. The derivative of the first function first, the derivative of 3x is 3. This is where we keep the first function the same. Then we keep the second function the same, and then we do the derivative of y with respect to x. We've actually already done the derivative of y with respect to x, that is dy dx. All right. Well then, are we done? You're like, dy dx, we found it. Well, there's actually a dy dx buried back here too, and somehow we'll need to bring them to the same side. We really don't want to complicate this side much more, so we actually don't want to divide this over, even though you might be thinking that, because then it'll trap the dy dx, and then you'll have this one over here. What I found is probably the easiest is to actually take this and distribute it against the 3y, and distribute it against the 3x dy dx. And so I'll show you what that looks like. Again, write small. So dy dx equals, and then I'm going to take the 3y that's right here and write it out front and multiply it by the cosine of 3xy that got multiplied inside. Plus, now we're going to take the second part, which is our 3x dy dx, and multiply it by the cosine of 3xy, what we're multiplying inside. And although this looks scary and intimidating, you're like, those are the craziest terms ever, you're right, but there's only 1, 2, 3 terms. And if there's only 3 terms, then life gets a lot easier if we're trying to isolate a term or part of a term. The first thing I think I'll do is probably take this monstrosity and move it over to the left side. So dy dx minus our 3x dy dx times the cosine of 3xy. And you might be wondering, well, wait, why did you move that term over there? Why just that one and not the other one? Well, think about what they have in common. Now I have 2 terms on this side, and they each have the thing that I'm trying to isolate, that dy dx, in common. So let's factor out the dy dx from each of these terms. So dy dx, I should probably put this on the outside so this doesn't become too confusing here, dy dx, and then on the interior, let's think about actually what stayed the same so I don't overcomplicate. We have a minus, that won't change. On the interior, we still have 2 terms. So we have to think, well, dy dx times what gets you dy dx? So that's definitely a 1. And then dy dx times what gets us this craziness up above? Well, it's everything that's there except for the dy dx. Now you're like, but doesn't that make things more complicated? Well, actually, no, we're pretty much done because dy dx is multiplying times this, and I don't care how complicated the right side becomes. I just need the left side to become isolated. So divide off the entire thing that's multiplying by dy dx, and that's going to give us dy dx equals 3y cosine of 3xy divided by this piece that I had in gold over here, 1 minus 3x cosine of 3xy. And we're done. Again, not the easiest problem. In fact, it's probably the most algebra that you're going to have to do this entire semester, seriously. But it's also not beyond you, right? And honestly, if you're okay with this first step, and this first step I think is by far the trickiest, then you're doing fine. The rest of this is all algebra, just moving terms around. We can work on that. This first step is the most important, realizing there's a chain rule and a product rule buried in the problem. That is definitely tricky. So on this last page, you have 3 problems to try, and at this point you should be doing okay, but please go ahead and pause the video, try it, and then once you have tried all 3, or you can do one at a time, pause, unpause, sounds good, then unpause and see how you did. All right, you're back. Now, C took some pity on you. C says, evaluate the derivative, but don't isolate dy dx. I'm like, sweet. There really only needs to be one step here then if we're just taking the derivative, but you will definitely want to write small. So the derivative of e to the xy. We're like, yes, e's, those are like our easiest derivatives. Okay, so the derivative of e to any power is always itself. It's e to any power. But then all that took care of was the e part. So I still need to multiply by the derivative of the power. And x times y are multiplying together, so that really suggests a product rule. So I'm going to go ahead and set up my product rule over here. And you'll notice that I definitely did not take my own advice and write small enough, but that's fine. Product rule rise, do the derivative of the first, keep the second the same, keep the first the same. The derivative of y with respect to x is dy dx. Cool. Equals, okay, and so this is just going to be like right here, and then equals, well, now we do the derivative of the other side, and the derivative of the other side, e to the 4x, it stays the same, that's always the derivative, but then we need to compensate for the power, so the derivative of 4x is 4, minus e to the 5y stays the same, always the derivative of e stays the same, but then the derivative of 5y, well, 5 stays the same, but when we did the derivative of x here, it became 1. The derivative of y is dy dx. Okay? So if I wanted to write this a little bit nicer, let's see what I can do. It'd become e to the xy times y plus x times dy dx. That's the entire left side simplified down. And then the right side I'd probably write as 4e to the 4x minus 5e to the 5y times dy dx. That's as far as we need to go. Could you isolate dy dx? Of course you could. You could distribute this in here. You could take the two terms with dy dx, move them to the same side, factor out, do all that fun stuff, but I don't want to. We can do the crazy stuff tomorrow when we get more practice in. So that's as far as we're going for today. Let's go ahead and look at the last two. Find the second derivative and then write your answer in terms of x and y. Well, we should probably find the first derivative, so I'm going to go ahead and do, well, yeah, we'll try to maybe divide this into a couple parts. I think this might become important, and then, yeah, do something like this. That'll be all right. Might not even need that last one. So, first step, if we want the second derivative of this equation, we don't even have the first derivative, we should probably find d dx of each side. It seems like a thing, right? We've done x squared plus y squared before. It's 2x plus 2y dy dx equals 0. Cool. Now, because they asked us to find the second derivative, to me that means it's probably going to be helpful if dy dx is isolated. So I'm going to go ahead and isolate dy dx. So let's see, 2y dy dx equals negative 2x. And then probably divide by 2y, so dy dx equals negative 2x divided by 2y. And simplifying even further, I think we just get negative x divided by y. Now, sometimes people say, well, wait, can I take d dx of this equation right here to get to the second derivative? And the answer is yes. But be warned, it's going to get a little bit weird because you have 2y multiplying times dy dx. So you're going to have to use the product rule in here, and sometimes people struggle with the product rule with two extra variables that aren't x. So I think it's usually, if you need the second derivative, easier to isolate and find the explicit first derivative first. Because if I want the second derivative, well, then I think that means that I'm going to have to do d dx of each side here. So d dx of dy dx and d dx of negative x divided by y. Well, this left side, I really shouldn't have drawn this line, I was right. This left side, we can think of it as multiplying. It's really not, but that's fine. And it becomes the d squared times y, and then the dx is multiplying times itself, so that thing's squared. Again, you could put parentheses, but nobody does. But then the right side, even though it looks nice and simple, we have one variable dividing by another. I think, to me, then, that means that we'll probably need the quotient rule. So let's set up that quotient rule really quickly, something like this, right? And then it's all divided by the denominator squared. Let's get to it. The derivative of negative x is negative 1. Keep the other one the same. Keep the top the same. The derivative of y is dy dx. And then I think that honestly looks pretty good, doesn't it? Well, except for one thing. The directions told us write your answer in terms of x and y. And in terms of, and maybe I should define this somewhere, in terms of really means that your independent, need that song, right? That the independent variables are x and y. However, if you look at this equation down here, I have 3 independent variables. If I wanted to find the second derivative somewhere, I would need an x, a y, and the value of dy dx. There are 3 independent variables. This is in terms of x, y, and dy dx. And so that doesn't actually meet the criteria for our problem, for our solution. We need to just have x's and y's, which means that this is a little obnoxious. So let's simplify this at least a little bit. We don't really need to clean this up, but I'll do a little bit here. This will, of course, become negative y, and then we have 2 negatives that turns into a positive x times something. We'll get back to that, divided by y squared. But what do we do with dy dx? Well, wait, we know a way to replace dy dx that only has x's and y's, because we know dy dx is negative x divided by y. And that is probably as good as we need to go, I think. You could simplify this further. In fact, what someone might do is they might say, oh, I don't like this y here, so what if I multiplied this whole thing by y over 1 and this by y over 1? So if you wanted to go a little further, you'd get negative y squared. These would cancel, so then y squared came from over here. Minus x squared divided by y cubed, and that would be totally fine. Maybe that's the nicest derivative. However, it would be fine to leave it here. You don't have to do that. I just always like to get rid of those complex fractions, but here is a nice implicitly defined second derivative. Or I guess an explicit second derivative defined in terms of x and y. Alright, last but not least, find all equations of the tangent line to the curve x squared plus xy minus y cubed equals 13 when y equals 3. What do they mean, all equations? Well, let's just set this up first. It's going to get kind of weird in terms of setting up your tangent line here. So I'm going to probably do everything in terms of dy dx. So actually, let's just start with the tangent line. So I'm going to go ahead and say, well, I know that let's start up here. We know that our tangent line is going to be some slope times x minus some value plus, and then we actually know the y value here. It's kind of weird. They gave us the y, but they didn't give us the x. So we need to find both the x value and the slope. So let's do the non-calculus part first. Let's just find the x value. Right now, I'll come back to this. I'll use the room for now. So x value-wise, we know that we don't know x, but we do know that y is 3. 3 cubed equals 13. I'm going to work to the right just to save some room and get some symmetry in here. So this becomes x squared plus 3x minus 27. I'm going to move the 13 over. I know I'll need that later on. And then putting all this together, I think that gives me x squared plus 3x minus 40 equals 0. Well, now maybe you see why I moved the 13 over. We're going to have to factor this to finish solving. 2 numbers that multiply to get to negative 40, but also add up to get to 3. We know the larger number of the 2 will have to be positive. And I think 40, the 2 things that jump out at me are 10 and 4, but that makes 6 when you subtract them. And then 8 and 5. And I think 8 and 5 does make 3, positive 8, negative 5. So we actually find 2 x values here. We find an x value of negative 8 when we set this equal to 0 and positive 5. So that's telling us then that we're going to have 2 tangent lines. And I'll kind of do this down here. Well, I should probably do something like this. Might run out of room again, but oh well. So we're going to have our first tangent line. Do this. Our first tangent line is going to be at the point x plus 8, right, opposite of x, plus 3. And my second tangent line is going to be x minus 5 plus 3. They have the same y value, right? This isn't a function then, or is it a function? It could be still a function, I think, right? We have the different x's getting the same y. That's allowed. How do we notate the slope, though? Well, I really don't like to use f prime because there's no f in the problem. I don't want to use y prime because y is not isolated. I would probably go back and say we want to find dy dx at the point negative 8, comma 3. And same thing over here. We'd want to find dy dx at the point 5, comma 3. Okay, well, in order to do that, then I think we probably need dy dx. So let's go ahead and do that in the middle. To find our dy dx, our equation of the derivative, we will probably want to take the derivative first. So we need to do d dx of x squared plus xy minus y cubed equals 13. And I'm going to again work to the right just due to my limited space here. So we know x squared, that's 2x. I think xy is going to be a little trickier here. So it's plus, and then again I'll do kind of that big bracket because x times y is going to be our product rule. Okay, so derivative of x, keep y the same, keep x the same, the derivative of y with respect to x, minus, and then y cubed. Well, let's just use our power rule, 3y squared. But I kept y the same, so I need to multiply by the derivative of the inside, which in cases of x is 1. That's why you'd say x is just 3x squared, easy, because it's technically 3x squared times 1. This one is 3y squared times dy dx equals, and I forgot a ddx of 13 here, so equals 0. Okay? Well, let's clean this up slightly. So let me switch colors just so we can keep clarity. I have 2x. There's nothing multiplying by the outside of the parentheses, so let's drop those. Plus y plus x times dy dx, okay, minus 3y squared dy dx equals 0. Clean up 2 steps in 1. I'm going to factor out the dy dx from both of these. That leaves me with x minus 3y squared, and simultaneously I'm going to pull these two over to the right side, so that gives me negative 2x minus y. And then let's finish this off. So we find that dy dx equals negative 2x minus y divided by x minus 3y squared. Sorry for all the small space here. You might just use a separate piece of paper, but that's fine. There's my derivative. How does that derivative help us? Well, we need to find the value of the derivative at these 2 points. So here we go. We need to find dy dx at negative 8. So let's see, I'm just going to set this up first. I find that if I put in blanks first, I tend to put in the wrong variable, or the correct value for each variable. And especially if you're doing it more than once, it's easy to put in the blanks first, and then you can go back through and put in the numbers. Otherwise, I tend to substitute the wrong thing, and then I just get mad later on when I realize that the answer didn't work out. Something like that. Good. Okay, and then the x spot is coming first in each of these, and let's take a look at the x. The x here was negative 8 and negative 8. The x here is 5 and 5. And then the y came at the end, and the y is 3 every time. So 3, 3, 3, 3. Let's clean this up best we can. 16 minus 3 is 13. 3 squared is 9. It's 27. Negative 8 minus 27 more, I think, is negative 35. What a beautiful slope. And then over here, negative 10 minus 3 is negative 13. And then the denominator, we get 5 minus 27. I think 5 minus 27 sounds like negative 22, or double negative 13 divided by 22. So now I think we have enough to finish our tangent line. My first tangent line, again, has that gorgeous slope of negative 13/35 times x plus 8 plus 3. Awesome. And my second tangent line has the slope positive 13/22 times x minus 5 plus 3. So tons and tons and tons of work there, but still very doable. Kind of cool having 2 different tangent lines here. So this is our introduction to implicit differentiation. So if it doesn't catch perfectly today, that's fine. You do have independent practice. You should work through it. Come with questions next class. But the nice part is we're going to spend 2 more full class days on this, and we don't actually have anything else to learn. our next 2 class days are just more practice so that you can identify and design some shortcuts of your own, get more comfortable with when we use dydx versus when we use 1, and really just ask questions. So I know it's intimidating on the first day. Come ask questions next class, rewatch parts of the video, email me. You guys got this. I know it's tricky, but you'll be just fine with implicit differentiation.